Hi guys, so this video is going to look at question number 6 of paper 1 for the 2015 exam paper. So the first thing we're going to do is actually read out the question here, and if you look here, we've got a typical graph question. We've got a parabola and another parabola. So we've got two parabolas, and it says here the graphs of f of x is given by negative 2x squared plus 18 and g of x, which is some unknown, and they're sketched below. We can immediately see by the fact that there's a negative in front, that's this sad graph. So obviously they've told us, but you can see it nonetheless. This one's going to be a positive because it's a happy face graph. It says points P and Q are the intersects of points F, so Q over there, P over there, and R is the intersect there. S is the turning point, as we can see, and then T is the y-intercept of both that. Okay, so the first question says write down the coordinates of T. So we want to find this value over there. Determine the coordinates of Q. Given that x is 4.5 at S, determine the coordinates. So basically find out all the coordinates. Find A, B, and C, etc., etc. Okay. Right, so question number 6.1.1. In fact, let's just write down 6.1, and we know that f of x is equal to negative 2x squared plus 18, and g of x is equal to ax squared plus bx plus c. So 6.1.1, it says calculate or write down the turning points, the coordinates of t. And it says there that t is the intercept of f and g. So obviously, if you want to go work it out, you can simply say, well, f of x is equal to negative 2x squared plus 18. X is 0, so it's f at 0, negative 2 at 0 squared plus 18. You can clearly see that we have f at 0 is equal to 18. So you don't actually have to do the calculation. You can simply see that, well, the y-intercept is 18. I mean, because we know it is the y-intercept, the point has to be at 0, 18. So you can just write 0, 18, but if you really wanted to work it out, that's how you'd go about it. 6.1.2, it says determine the coordinates of Q. So I'm just going to redraw this so that we don't have to keep flipping between the two. So we've got something that looks like this. That's our F graph. That's point T. We've got another graph that comes in like this. That's our G. Obviously 0. That's P, Q, S, and R. Let's just add the little X and Y's. Right, so there's our graph, and it's so we know what T is. T, we said it's J. T, we said, was 0 and 18. And then it says determine the coordinates of Q. That's this guy over there. And Q is the intercept of both those graphs, but you also notice that Q is the x-intercept, or one of the x-intercepts of f. So we know that if we want to find the x-intercept of a parabola, of any graph really, we write down the formula, negative 2x squared plus 18, and the x-intercept, that means y is 0, negative 2x squared plus 18. You solve for that, and we get 2x squared equals 18, x squared equals 9, just do, and then x equals plus or minus 3. It's very important that when you square root both sides, so we square root that side and we square root that side, this becomes a plus or minus, right? There has to always be the two answers, and that makes sense because there's a plus 3 and a minus 3. So Q is 3 and 0, so we found the coordinates of Q. So it's Q is 3, write it over here. Therefore, Q sits at 3, 0. Obviously, we know the point P. P sits at negative 3, 0. So we write those down. Okay. 6.1.3. It says, given that x, let's just write it down, equals 4, 5. In fact, I'll go over to it now. At S, determine, so let's just write here, at S, determine coordinates of R. Just make it a little bit nicer, of R. Okay, so just to show you guys, it says given that x is 4.5 at S, determine the coordinates of R. So we've done 6.1.1, done 6.1.2, and 6.1.3 gives us that. Now, they're saying that at S, at this point here, we have 4.5. That's our x value. And in order to figure out that R, we need to figure out the y equals 0. So we need to do the same thing as we did over here, but we need to do that with the g of x formula. So what that means is we first need to figure out what g of x is. There's another way we can do it if you don't want to work out g of x, considering it's only a 2-mark question. So it's probably better if we don't work out g of s. We've got to say, well, s is the turning point, and that means that if we have a graph, say whatever, I'm going to draw the same graph, but any parabola, and we've got that turning point there is, in this case, we called it x, and the distance, if we call that, in fact, let me just use a different color, makes it easier to, well, that's useless, easier to see. But if we got a point there and a point there, well, it's not quite drawn straight, so let me, sorry about this, just draw that a bit better. Okay, so that's our x point, and the distance between that point and that point, and that point and that point must be the same. So if this is distance a, then that must also be distance a, because it's symmetrical. It's symmetrical around that turning point. So what we can do then is say, well, if x is at 4.5, do we know what the first turning point is? That's a turning point, x-axis cut is. Do we know that point? Well, if we look at the graph, that's Q, and Q is sitting at 3. So maybe not in this specific graph. Let me just draw that out. That point is at 3, and that means that 4.5 minus 3 is going to be the distance between that intercept point and the line of symmetry, which is this line here. And it's the line of symmetry because it's the turning point of a parabola. So 4.5 minus 3 gives us 1.5. In other words, the distance from that 4.5 to the next cut must also be 1.5. So if we have 4.5 plus 1.5, because it's on the other side, we must get 6. So that tells us that while this point is 3, 0, this point must be 6, 0. So now we know what that point is, and point R is sitting at 6, 0. Now once again, you could also have worked out the equation and calculated all that, but there's no need if you just for 2 marks. The next thing says determine the values. 6.1.4. It says determine the values of x for which g double dash of x are greater than 0. Now that means the second derivative. Okay, so if we look at the second derivative, how do we look at the second derivative? Well, we don't even know what the first derivative. We don't even know what g is. Well, let's just write g. G of x is equal to ax squared plus bx plus c. Now, without knowing what a is, without knowing what b is, and without knowing what c is, obviously we can solve for that. That's not a problem at all. But let's have a look. We can just say g dash of x is equal to 2ax plus b. Right? We solve for that without knowing the values. We just solve, and g double dash of x is equal to 2a. Right? And then we said, well, the graph actually looks like this. It's the happy face graph. So the graph looks something like that, right? And what this tells us is, if you remember correctly, the second derivative tells you the concavity. If, so just a note on concavity here. If the second derivative, so g double dash of x, or f double dash of x, or whatever it is greater than 0, then we have concave up. And if g double dash of x is less than 0, we have concave down. Okay, so concave up, concave down. So this one is clearly concave up. And if that's concave up, that means that the second derivative has to be positive. And we can see here, we know that a is a positive value because it's a smiley face. So simply because it is a smiley face, we know that a is bigger than 0. And if a is bigger than 0, and we look at the second derivative over here, that means the second derivative, g double dash, is also bigger than 0. And we can also look at it and say, well, actually we know it's bigger than 0. We know it's bigger than 0 because it's concave up. And the question originally was, for which values of x is this thing bigger than 0? So we don't even have to do any calculations. We can simply say, well, because it is concave up, it is bigger than 0. Therefore, for any values of x, this thing is positive. So the answer for this is just simply x, any real number, because there's any real value for x is that. You could also say x between negative infinity and infinity. So that's actually quite an important little thing, this concavity. You can see the concavity by taking the second derivative and saying, well, if the second derivative is positive, then we have concave up, and if the second derivative is negative, we have concave down. 6.2. So let's just take a look at 6.2. 6.2 gives us, it says, the function is defined as that, so we've got a hyperbola, and it has the following properties. They've said the domain is that, y-axis is that, and okay, so we'll draw it. Now I want to draw a neat sketch, so let me just write it all down. They said here that our formula is y equals a divided by x plus p plus q, and then they've given us conditions. The domain, so they said domain is x any real number but x not equal to 2, negative 2. They've said, they've said y equals x plus 6 is an axis of symmetry. They said the function is increasing for all x. So number 3, the function is increasing for all x not equal to negative 2. draw a neat sketch including everything. So just there's something we need to discuss before we even go on here about hyperbolas. So I'm going to put a little note over here, and this is very important. If we look at the y equals a over x plus p plus q, this q value, that is the vertical shift. So if we draw our graphs, the standard graph looks like that, and like that, and like that, and like that, where our asymptotes are at 0 and 0, so x 0, y 0. If we apply a q, that q value becomes this shift. So let's say it's a positive q value, it becomes a positive shift. So that's q. If it's a negative q value, it's a negative shift. So it goes here, and that's negative q, whatever the q value is. And that's our asymptote. So this q value here is our horizontal, or our y asymptote. Okay, so we've got our asymptote. What about this value over here, this p? Well, that p value defines where our graph cannot be, the domain of our graph. So if we look at this as a function, we've got a over x plus p. It doesn't matter what the q is. Well, let's just put the q in, just for completion's sake. If we make y equal 0, in other words, where it cuts on the x-axis, in other words, y is 0. So 0 equals a divided by x plus p plus q. If we have no q value, so q is 0, then you can clearly see then that we've got, so plus 0, we've clearly got no way of making this 0, so the asymptote, which is your q value, is 0, which is why we normally get a 0 asymptote. If you have a q value, then obviously it shifts up and down. But what happens if we make that x 0? So y equals a over x, and let's make that p value 0 plus q. Then do you agree that if x is 0, if this guy is 0, then we have a divide by 0 problem. So it's going to be a divided by 0, whole big problem, so we can't do that. So that's why we have a horizontal asymptote and a vertical asymptote. But now we've shifted it, so we have this y equals a divided by x plus p. And what that tells us is that if this bottom piece, this guy here, is equal to 0, in other words, x plus p equals 0, then x must equal negative p for it to be divided by 0. So if we want to divide this by 0, x must equal negative p. In other words, the x asymptote, or the vertical asymptote, is the negative of that. So if we have x plus 1, then the vertical asymptote is minus 1. If we have, for example, y equals a divided by x minus 2 plus q, then x equals 2 is our vertical asymptote, because we need to make x2 for this to be divided by 0, and then we've got the problem. Another very important thing that we must mention is the lines or axes of symmetry. And the axis of symmetry, specifically with these types of graphs, is actually remarkably simple to figure out. The axis of symmetry, we look at the formula, y equals a divided by x plus p plus q. And the axis of symmetry is simply a straight line graph, because remember, we have our graphs, we have one axis of symmetry there, and we have another axis of symmetry there, and it'll shift around as your asymptotes shift around. But the point is, this is y equals mx plus c, and this is y equals negative mx plus c. Some two straight lines, one's a positive, one's a negative. Okay. If we then decide to say, well, what are those axes of symmetry? So it's remarkably easy in the fact that we simply go plus or minus x plus p plus q. So we don't even care about this a value. That doesn't make a difference. The axis of symmetry is simply whatever's at the bottom, in brackets, plus or minus, and then plus q. And then sometimes they'll say, well, give the positive axis of symmetry. In other words, one of the positive gradient, which is going to be y equals, and then you just look at the positive, x plus p plus q. So whatever that works out to, and the negative one will be y equals negative x plus p plus q. So you literally just take the values that's at the bottom. So x plus 5, for argument's sake, put that in the bracket, and then put this little plus or minus. So this guy here is your axis of symmetry. And then obviously that splits out into this one and that one for the positive, negative gradient, positive gradient. And if you look here, positive gradient, negative gradient. And it's as simple as that. Right. Now, if we go back to the actual question, which was the domain is anything except for x not equal to negative 2. So in other words, they're saying if we have a y equals a over x plus 2 plus q, that tells us that x cannot equal negative 2, because if x is negative 2, then this whole thing bombs out. So we found out what our p-value is. Then they said this is an axis of symmetry, okay, x plus 6, and that's the positive axis of symmetry. So that's this guy, the positive axis of symmetry. So y equals, and they've said it's x plus 6, but we know that that's equal to x plus p is 2, plus q. So we can see here that while the x's cancel, we have 6 and then 2, so it's 4 equals q. So now we've solved our p problem and our q problem. So we have, therefore, y equals a divided by x plus 2 plus 4. So does it actually matter what our a value is? No. All it matters is that they've told us that it is always increasing. So let us have a look. If we take that and we plot it on a set of axes, we have 4. In other words, we have an asymptote at 4. We have an asymptote at negative 2. Remember I said it's the opposite because x must equal negative 2. So we have an asymptote at negative 2. And then we've got to decide, is it going like this or is it going like this? So if we look at it doing this, is that function increasing or decreasing? And same for that one, because obviously if it's on the one side it must be. This function as we see it is decreasing. Why? Because as x gets bigger, so x gets bigger, you could write that differently, x tends to infinity, y gets smaller, right? Tends to, in this case, 4. Same as this, as x gets bigger, going from the other side, y tends to negative infinity. In other words, this is a decreasing function. So this is a problem. We wanted an increasing function. So we'd have to draw it slightly differently. So we have the same thing. We have negative 2 as our one asymptote. Whoa. Let's draw that a little bit neater. It was horrible. We have negative 2, and the other asymptote we said was 4. And if we draw it like this, let's just make it a nice pretty color, like that, and like that, we can see, this one is increasing. As x goes to infinity, right, this thing, your y value, tends to 4, so it's getting bigger and bigger and bigger, all the way up to 4. And on the other side, on this side over here, as x tends to -2, because it's going towards the asymptote, y tends to infinity. So now we have an increasing function for all x. So that is the graph. So that's how we can draw this graph, and that's it. So we know it's increasing. We found our two asymptotes because they told us the asymptotes, and that's it. So not too difficult, provided obviously you know your basics about hyperbolas. And that is question number 6.